Welcome to a brief lecture on the topic of finding FIR parameters. We will discuss the covariance of signals of LTI systems, an FIR model. We will explain how to use ACF and CCF for identification. We will conclude with an example and Scilab code. Let's recall the identification problem. Gn is the impulse response and capital G is the Z transform of that. Here is the plant. Un is the plant input. Yn is the plant output. Cn is the white noise. Hn is the impulse response of the noise model. This capital H is the Z transform of this small h, and we get the plant output as given by this. The path from U to G to this summing junction is denoted by Gn convolved with Un, whereas the second one is indicated by Hn convolved with Cn. Recall that we are talking about having all the signals Un, Vn, Cn, Yn as different from the plant model G and the noise model H. The identification problem is the determination of model parameters, namely G and H. Determination of G and H given that you have U and Y. So let us start with the model we had in the previous slide. Let us convolve both sides with U of 0. We get this expression. So Y is the first index in the subscript and U is the second one, and the difference between n and 0 is n. So we get this gamma Yu of n. Nothing happens to Gn, but then Un, when it is convolved with U0, you get gamma Uu of n. The difference between these two is once again n. But U and C are uncorrelated. C is white noise, U is the plant input. As a result, when you convolve with this, this becomes 0. Now, if the input is chosen such that its autocorrelation is an impulse, we get this expression. Gamma Uu of n equals k into delta of n. Namely, if this n is anything different from 0, then the right hand side will become 0. And from this, you can determine this gamma Yu. How do you do that? You can just substitute here, and so when you substitute convolved with impulse, you will just get k here, it becomes k into Gn, and using that you can calculate Gn to be 1 by k times this gamma Yu, which is the expression obtained here. So this comes just from the definition of what an impulse is. From this we also see that if you know gamma Yu, that is the cross correlation, cross covariance function, then you can find Gn, provided you know this k and this U is done, this U is chosen in a particular way. Now how do we get this? One way to realize the impulse function is with the help of pseudo random binary sequence, which is abbreviated as PRBS. PRBS takes the value of either 1 or minus 1, and one can show that the ACF of the PRBS is an impulse function. So we shall use that shortly. Now let us consider the following FIR model, where we have used finite impulse response model. In other words, this G has a finite number of non-zero entries. Let us apply the meaning of convolution. We get this where we have assumed G to have n plus 1 non-zero entries starting from k equals 0 all the way up to k equals n. Because n is a finite number, we call this a finite impulse response model, and there are n plus 1 terms in this summation. Now let us expand this. This is the expression I had. Let me expand the summation. There should be n plus 1 terms, and these are the n plus 1 terms starting from 0 going all the way up to capital N. Now let us multiply by u of n and take expectation. The difference between these two indices is 0, so we get gamma over u of 0, and you get this. Now I have chosen it in a particular way so that it becomes, you get minus 1, minus 2 and so on all the way up to minus n, but notice that you could have, because it is gamma uu, it is ACF, you can have either minus sign or plus sign, it does not matter, but I have written it in this particular way so that it is easy to remember the way I have written this. Let us multiply by u of n minus 1 and take expectation, and so that means we are multiplying this y of n by u of n minus 1, and remember this n minus 1 is a smaller index compared to this n. So as a result we will get gamma yu of positive 1, and this is not 0 because this n minus 1 occurs first. As a result of that yn changes, right? U occurs at n minus 1 and the response is at the next time instant n, and you see y changing. So it is okay to have this, it does not violate any causality principle, and we get gamma yu of 1. And here we started with 0 and ended up to minus n. Here we start at 1 because the difference between n and n minus 1 is 1. Here also there should be n plus 1 terms. There are n plus 1 terms because you have g of 0 all the way up to g of n, so there are n plus 1 entries. Here we started 1, so we should end at 1 minus n. Here also we had n plus 1 terms, here also we had n plus 1 terms. Notice this whole thing is shifting, we are adding 1 to each entry. Plus 1 it becomes 1 here, plus 1 it becomes 0, plus 1 it becomes 1 minus n. You continue this way and finally arrive at u of n minus capital N, multiply both sides by this and take expectation, and you get this. I would want you to verify that all these entries come out to be this way. What we are going to do now is to represent these equations in a matrix form. So let us do that. So you get this expression. How do you check this? Look at this first equation, you multiply this with this and you should get the first equation here. G0 times gamma u of 0, G0, G1, Gn, which we had as the vector here, and this vector multiplies this row vector 0 to minus n. You can see here 0 to minus n. The next one, of course, we started with 1 and ended at 1 minus n, which is what we have. Started at n, started at 1, ended at 1 minus n. Once again they multiply the whole thing. Remember we started with gamma yu of 0, we went all the way up to gamma yu of n. One can check that there are n plus 1 entries here, there are also n plus 1 entries here, and there are n plus 1 entries in a given row. Also notice an important fact here, the unknown here is this vector consisting of these elements G0 to Gn, whereas these gammas, the ACF and the CCF, are obtained from the plant by doing experimentation, by exciting the plant with a signal and taking some averages, we get this vector and also this matrix. So as a result, this is extremely useful approach in practice. You are given a plant, you are given a black box, you don't know what is happening, you excite it with an input, measure the output, take some averages, and from there you can calculate this G, which denotes the impulse response coefficient of this plant model. And remember that the impulse response has all information about the plant. As a result, if you can determine this, you know everything about the plant, all that you can get just from experimentation. Of course, for that to happen, you want this matrix to be invertible, okay, which is what I have written. For the calculation of G, the ACF matrix should be invertible, and this is known as the persistent excitation condition, and it is made possible with the help of the PRBS input that we mentioned earlier. Here we take an example, identification of FIR process, generate PRBS input UN, white noise Cn, and the corresponding output Yn for this system. Here is the plant model, here is the noise model. We have taken this to be white noise appearing directly here, and we are asked to determine the underlying FIR model from the input output data. That is, generate data, and given the data, determine the model. At that time, pretend that you don't know the model. So let us expand this in power series. Let us take this denominator term to the numerator, and the power series expansion is this. When I multiply these two factors, I get this expression, and because it is a decaying sequence, in fact a fast decaying sequence, it can be approximated well by a FIR model. So the problem statement is, excite this plant with C and U, measure Y, based on these measurements determine the model parameters and check whether what you determined agrees with the system that you have here. That is the problem statement. Here is the Scilab code given. It's in a file FIR underscore CRA underscore ex1.sce. It makes use of Scilab built-in function called RMAC. It also uses CRA.sci, which is given here. So with the help of all this, you can get this C and U. Notice that U is a PRBS signal. It takes values of -1 or +1, whereas C is white noise, and you get the corresponding plant output here. I would like to point out at this point that you get these kind of measurements naturally in the plant measurement. Of course, PRBS does not happen naturally. You will have to excite the plant with that. Such a small excitation is often permissible. What is more important to realize is that these signals, which seem to be useless, seem to contain no information at all, actually have all the information we want, which can be demonstrated, which will be demonstrated in the next few slides. In fact, all that you need is this last slide, where we have compared predicted and estimated coefficients. In fact, if you execute the Scilab code, you get this, and the actual values that were used to generate the data are given by this black dots, and the estimated ones are given by these circles, open circles, and notice that they are very close. In fact, they are the same. There is no difference between them as far as statistical properties are concerned. As a result, we say that this is in agreement with what is expected. So here is an example of a system that is excited by signals and plant output measured, and with the help of the Scilab code that I showed earlier, you obtain the FIR coefficients, which are pretty good. So this demonstrates the power of this method. We will see more such examples in subsequent videos. We will also consider other noise models. In this case, we just used an FIR model. We will use other types of models as well. I would encourage you to carry out the Scilab code execution and verify you get the results shown in this video. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.